Hello everyone, my name is AL-Maidan. I hope you are all fine. Today I'll be talking about Snell's law, total internal reflection, and fiber optics. Let's get started with Snell's law. Snell's law. Will Abraham Snell's Dutch astronomer and mathematician. Snell's law shows the relationship between the angle of the incidence and the angle of refraction, as you can see here. N1 times sine theta 1 equals N2 times sine theta 2. N1 and N2 are the refractive index, theta 1 and theta 2 the angle of incident and the angle of refractive. This is an example here. When light passes from air into water at an angle of 60 from the normal, what's the angle of refraction? Given index of refraction for air, as we know, is 1, and the refractive index of the water is 1.33. Theta 1 is given in the question 60 by using Snell's law. We get this equation. We must find theta 2. Dividing both sides by N2 got sine theta 2. Putting the numbers. Sine theta 2 equals 0.6511. Take the inverse, sine inverse, this number. The angle must be 40.62. The second point of my presentation is total internal reflection. Total internal reflection occurs when light reflects off the inside walls of the denser medium. We have two conditions for the total internal refraction. The first one is the light must travel from the denser medium to the less dense medium, and the angle of the incident angle must be greater than the critical angle. It will be shown like that later. When light travels from a denser medium to a rare medium or less denser medium, if the angle of the incident is greater than the critical angle, the ray returns to the denser medium. This is known as total internal reflection. Okay. Oh, it goes back, sorry. First condition, the ray is traveling from the denser medium to the less dense medium or the rare medium. If the angle is less or smaller than the critical angle, the light will be refracted inside the air, the less denser medium, and the angle will be bended away from the normal. If the angle is theta 1 equals the critical angle, the light will follow a path along the surface of the denser medium, as you can see here. If theta 1 or the incident angle is greater than the critical angle, the light will be reflected inside the denser medium, and this is the total internal reflection. Two conditions, as I mentioned: light traveling from denser medium to less dense medium, angle is greater than the critical angle. If the angle is less than the critical angle and the light is traveling from denser medium to less dense medium, the ray will be reflected, the ray will be bended away from the normal. On the other hand, or vice versa, if the ray was traveling from the air to the glasses, here the light will bend it closer to the normal. When the incident angle increases, the refraction angle increases as well. Why? Denser medium, less dense medium, the ray will be bended away from the normal till it gets to the critical angle. At a certain angle, which is the critical angle, the light will follow a path along the denser surface. Here we mentioned about that before. Here's the critical angle. The light will follow a path along the surface. But if the angle is greater than the critical angle and light wants to travel from denser medium to less dense medium, the light will be reflected here. Total internal reflection, as you can see here, will be reflected inside the denser medium. First condition, water is denser than air. The angle is greater than the critical angle, so the light is reflected inside the second medium. Last point of my presentation is total internal reflection. Optical fibers. Optical fibers are just reflective tubes. They can guide the light inside the fibers for long distances. The walls don't absorb any light, so all the light will be reflected inside the walls, and we can can also carry a huge amount of information throughout them. This photo figure showed the fiber tubes, total internal reflection inside the tubes. The light is reflected inside the tubes many times till it gets to the desired point. And thanks for watching. I hope you are fine and to be fine. Good luck with your exams.